questions before we go forward? Any questions from previous classes?
Sir, I have one question.
Yes, please. Comments. Yes. Switch
Like,
on your video if possible when asking questions.
okay.
I can see who are on.
So can you see me now?
Yeah.
So in the last modeling, like when we considered the capacity of the environment, so we placed some limits, right, on R. So that was 0 to RM,
Yeah.
or RM plus 1.
What is RM plus 1? Sorry.
So RM, you consider that
Maximum.
the maximum limit on the birth per individual per generation.
Yeah, that was the max. Yes, absolutely.
So that was about the birth rate on the birth. But when we
But it
collated
had
birth,
no, it had both birth and death. It was B minus D plus 1.
okay, so that limit was RM plus 1, right? So
okay. The maximum it could take R0. The maximum that R0 could take is RM plus 1. Yes, yes.
yes.
Unfortunately, I wasn't. I wasn't very careful when defining these things. But I hope you all got what I meant. Okay,
Yes.
go ahead.
So when we modeled that using a linear relation, at last we modeled one equation, right?
Yeah, we wrote a linear equation. Yes,
So
absolutely.
in that case, we considered the maximum limit as RM, not RM plus 1.
How? So I'm unfortunately sorry. What I should have really done was that line is connecting from R0 to 0. R0 when n is equal to 0.
Okay.
Okay. And then it reaches 0 when n is equal to k.
Okay.
So that should have been the equation I should have written. And
yes.
Where R0 can take a maximum value of Rn plus 1.
Okay. So
that should have been consistent with what I have been saying, but I messed up a bit. So I said, let it decay from Rm to whatever, Yeah, yes. I messed up a bit while I wasn't very consistent when I was writing this.
So actually the question is, you gave us an exercise of varying RM or the initial conditions, right? In the last lab.
Yeah.
So there we found that at particularly RM is equals to 1, there like the population goes to extinction. So
RM is equal to 1. Okay. I mean, basically should have been R0 the way I'm now defining. Okay, fine. Okay.
So, okay, yes. So you can say that R0. So R0 greater than 1, the population actually grows up and reaches some level.
Finite.
But for R0, 1 or less than 1, as I have got it from my group,
yeah.
So that would be goes to extinction.
Absolutely.
So when we trace it back to RM plus 1, so RM plus 1 is equals to R0.
Yeah. No. So please, I messed up when I was saying this. So I'm really sorry about that. Maybe I'll just maybe write that clearly now. Is that if it's okay?
Okay.
I think you're absolutely right. I wasn't consistent in my notations at all. I think that would have caused unnecessary confusion. Let me just share my screen and make it clear. Okay.
Sure.
Okay. You can also see the window, right? My screen, right? Okay. So fine. Okay. So if we think of the basic question at hand, we would like to understand how population changes over time. We wrote that this, is of this form in the simplest consideration. Okay. And then we considered a case where R is equal to constant, right? And in that there were sort of 3 other cases depending on the value of R. There was either an extinction, which happened when R was less than 1, right? Sorry. Then constant or an equilibrium population when R was equal to 1, and an explosion which basically corresponded to an exponential growth when R was greater than 1, right? This is what we found. And we found that while extinction and equilibrium are indeed in principle possible, explosion clearly cannot happen forever. And we all understood why this was happening. R was in some sense, R was basically the number of births minus the probability of death plus 1. Okay, the plus 1 represents the fact that there are individuals from the previous generations, right? So B minus D is what's happening to that generation. Okay, it's a number of individuals born per individual and per generation. D is the probability of death of that focal individual per generation. So we have this expression for R. Okay, now we understood that this cannot remain same value across generations, because these birth and death rates will depend on how much resources are present. And as the population size increases, these resources will go down, and therefore the births and deaths will go down, right? So what did we do? We made a modification. We said R is not a constant anymore. So this is, let's call this case capital 1 to distinguish from the cases 1, 2, 3 that I had discussed earlier. So we considered case 2 where this R now decays as a function of n. Okay, and we said, let's say it has a value of R0 when the value of population size is 0, and then it decays. There are, of course, many possible decaying functions. We arbitrarily chose out of a straight line. So when value of nt is k, R becomes 0, and if we do that, basically we are now assuming that R is not a constant anymore, but R follows an equation of this form. Okay. Now in this entire business, there is really no role for RM, by the way. Okay, RM was basically, I was talking about RM primarily to think through all parameter values and what is the range of values it can take. So what we then did was, what are the range of values that R take, right? Okay, R basically can take, the range of values that R can take, we discussed, could be as small as 0, but it cannot be negative. And we said the maximum value it can take is when B reaches a maximum value. Okay, whatever the maximum number of births per individual possible, and D is 0, nobody dies. So therefore D is equal to 0, whatever the B max plus 1. So if you really ask me, I should have done something like this, but I messed up my notations in a really horrible way. First mess up I did was I used R0 instead of B when I was deriving equations. So I'm really sorry about that. Let's stick to this. And in fact, this is something, a clarification I wrote down in the assignment, in the instruction on the assignment. So I hope this will resolve the issues, forget RM entirely. Okay. So technically RM is basically BM plus 1. Is that now clear?
My question here is the R0 in this modeling exercise, that R0 can be BM plus 1, right?
Yes, R0, the maximum value of R0 is BM plus 1. You're right. Yes.
So, okay. So when we did perform that numerical analysis of this particular equation, so there we got that R0 should be greater than 1 to reach a non-equilibrium state, non-zero equilibrium.
Non-zero equilibrium state, yes, right.
So in that case, BM should be greater than 0.
Yes.
So that is always the case, right?
No, but assuming D is 0.
Assuming?
See what, when do you reach a value of RM max or maximum? RM is maximum is BM plus 1 when D is 0.
Okay.
Right? That's of course never true.
Okay.
Well, actually, it can be true. If think of, maybe, cellular populations, death there is, if each cell is dividing into 2 daughter cells, under the assumption of, sufficient resources, they don't die. I mean, in that case, yes. But, of course, that's a very idealistic scenario. But, D is, so it was under the case of D is equal to 0.
Okay. Like, actually, I was tracing it back to BM, and I was wondering, like, BM should always be
always
0.
Yeah, true. I'm sorry.
So that would be always the case.
I understand the source of confusion. Absolutely, no problem. Sorry, it was entirely my mistake. I messed up in my notations. Any other questions before we go forward? Okay, so this is
hi.
Yeah. Who's this?
No, I just want. This is Pranav.
Okay.
No, I
Hi,
just
Pranav.
wanted to. Hi. I just wanted to clarify something that Paras said. Did he say that, like, if R not in the new model that we built that day using this declining R, when R not is greater than 1, that it will be equal. I think that's what Paras
Paras said
said.
you will reach a
But,
finite equilibrium value. Finite meaning in a non-zero equilibrium.
Yes.
Yes.
Yes. So I
That's what
just
he
wanted to say that actually it shouldn't be R naught in that case, but the entire R would have to be greater than 0. So R naught would actually be, so in the exercise that we did that day, we found that since R naught is R max and that whole expression, that would have to basically be 1 for it to
entire
become.
expression has to be 1. Is it? Okay.
Yeah, I don't know if
I mean R naught times 1 minus NT by K must be 1. Is that what you're saying?
Yeah. Yes, that's what I'm saying. Because we are substituting
that does seem right. Yes, that does seem right. At the equilibrium, that should be right. Yes, right.
Yeah,
absolutely right. Yes. Yeah. Okay, so that's a great point. So let's now move forward. You have already taken this very simple model. Let me now introduce a bunch of terms. So this form of writing, mathematical models of populations. Now all of us agree that R itself can depend on N. Is that right? Okay, so now I'm now making it more explicit, and I'm writing it this way. Is that fine? Let me go back and tell you what changes I have made. I am beginning with this. When we began, we assumed R was constant, but now in this case too, we know that R constant is just a very, very simple assumption that corresponds to unlimited resources, right? Right? That will not be true. R will decrease with N, right? Therefore, R will depend on N. So that's what I am now writing. NT plus 1 could in general be written in this form. R times R itself depends on the population size, and then you multiply this R by NT. This is a very general way of writing the equation. This R could be a linear decay with N, it could be an exponential decay, it could be a much more complex function, and that function will depend on the kind of biological process that are happening. Okay. Okay, and one thing, there are a few important things about this equation. One is that here we are assuming that the generations or the birth and deaths are happening at a discrete time step, right? Therefore they're also called discrete time population models. So I'm considering populations at generation intervals, so therefore they're called discrete time population models. Okay, and in this discrete time population models, so again, if you go back to the case 1 here, which I wrote as R NT is a constant, this corresponds to what is called density independent model. Density independent population growth. So why do we say that? So R is a measure of growth rate, and this growth rate doesn't depend on the population density NT. So therefore we call them density independent population growth, and the sort of most classic sort of statement that follows will be, in all density independent population growths you have exponential growth of populations. Okay, so you may say that growth requires R greater than 1. You're absolutely right. But growth can also be thought of as positive or negative. So in that sense, this statement is still sort of valid. We either have an exponential decay of population if R is less than 1 and is constant. You will have an exponential positive growth explosion if R is greater than 1. Okay. On the other hand, the cases where R is not a constant, depends on NT, they are called density dependent population models. Okay. So, and let us now move further. We have that page. And we considered this specific model last time. NT was equal to R NT times 1 minus NT over K. Okay. And this is called logistic population model. Okay. Of course, there are logistic population model comes in two varieties, and the one that we are looking at would be discrete time version. We will also, study the continuous time logistic population model. Yeah, somebody had a question. Yes.
Yeah, sir.
Sorry, NT plus one. Sorry, NT plus one. Sorry. Okay, yeah, go ahead.
So in the first case, I was thinking why do growth always has to be exponential and why can't it be linear increase?
Just 1 second. This also corresponds to basically unlimited resources when R greater than 1 case. Okay, say that again. What was your question? Was why is it an exponential growth? I think
Yeah.
that's something I covered in maybe the last class, right?
Why not? Why is it not a linear increase growth?
So I'm going to the previous class. Okay, so if you look at the previous class, page number 4, which I'm right now showing. So under the assumption that R is constant over generation, we found that NT plus 1 is R power T times N1, right? So, so this is, this form of the function is an exponential growth, right? Basically, for example, if R is 2, think of cellular division, right? At the end of one generation, one cell becomes 2, one bacteria becomes 2, then R will be 2. So you have 2 power T times the initial population size. So 2 power T is an exponentially growing function. If it's another organism where you have 3 individuals at the end of one generation, it would be 3 power T. That's also an exponentially growing function. It could be even 1.1 on an average. It doesn't have to be an even integer, right? On an average, an individual produces 1.1 offspring per generation. That would be 1.1 power T. That again is an exponential function. So any function, anything that looks constant power time, that's an exponentially growing function.
Oh, okay.
That's not a linear function.
Okay.
Right?
Sir, I have a question.
Yeah.
In this model, we are not assuming that individuals from 2 generations do not overlap, right?
Do they overlap or not overlap? That's a very good question. So here, do we assume, do they overlap? Let's go back to the first page here. So R is equal to B minus T plus 1. So if you think about just the entire mathematical formalism, that is not a necessary condition. Okay. For example, it is entirely possible that only half, D is half, which means that some individuals from the parent generation, half of the individuals from the parent generation are alive. As long as they also have the same fecundity as the new generation, new offspring who are just born, then this will continue to be true. But as you do know, that's a very unrealistic assumption. So, so usually these models are applied usually in the context of, you're right, you're usually D is equal to 1, right? At the end of one generation, the parent generation either has died or they're not fertile anymore. So basically what you have is that R therefore basically becomes B minus, what is it, B, basically effectively becomes B because, 1 and the D cancels out. And therefore you do have non-overlapping generations. But mathematically, it is not a necessary condition. If you can, produce a, species where, despite having a very discrete sort of, birth death process, if the parents and offspring have the same fertility rates. That's a very good question.
Thanks.
Okay. So, so now what do we do with this? We have done some simulations with this. So did I call this R0? Just let me stay consistent. Okay. Okay. So R is the entire function. R is 0 is the coefficient that I'm using here. So now what do we do with this? Now I asked you last time to do some simple simulations. So basically I asked you to use a computer to sort of to check how these numbers change over generation. And before we did something called a rescaling. Rescaling is a very useful technique in any mathematical modeling analysis. So mathematical models of biology often have large number of parameters. But to analyze them in ways that are tractable, we try to reduce as many variables as possible. Okay, and in this case, if we assume that xt is nt over k, we showed that we can write an equation of this form. So xt can be thought of as a a normalized population density where whose maximum value is basically 1. So we wrote an equation of this form, and then I asked you, please do some simulations. Why don't you just play with this? And I think when I was going through, I think all of you had found very interesting and correct results. And let us see.
Sir,
Yeah, please.
that was also making the equation dimensionless, right?
This also makes the equation dimensionless. That's a very good point. Absolutely, yes. Yeah.
Okay.
Okay. So shall I go forward now? Okay. So you did some simulations and found some results. Okay. And let's now try to do it in a mathematical way. Not a and let's see, can we say something about what happens with this equation? Can I make some mathematical predictions of if this equation was true in real world? If there was indeed a population that followed this equation exactly, can we make some predictions? So why do we do this? Why do we ask this question? The primary reason is that if there is a system which can be explained by equation, at least I must have a good grasp of that biological system. If I don't even have a good grasp of a system which can be explained by equations, I have no hope of trying to say something about a real system where equations are probably impossible to write anyway, right? So let's see, can we say something useful and interesting from this equation by a sort of analysis that mathematicians try to do. So one thing we described, a concept I described while explaining was that of equilibrium. Equilibrium is a state where things don't change. So nothing changes in sort of, in a very simplistic way. In the context of population model that we have, the population size, if we apply this concept, that means the population size remains constant at equilibrium. So at equilibrium, population size remains constant. Meaning, what does it mean? If there was some population nt, what will be the value? What is the population size at nt plus 1? It will be same. So nt plus 1 will be same as nt. If the equilibrium population size was, let's say, 120 individuals, it will be same even in the next generation. It will not change anymore. So what we then do is we denote such a population for simplicity by n star, because now there is no time dependence anymore. Okay. So, and we often want to know, is there an equilibrium population? Okay. And let us see if we can calculate this equilibrium population, assuming that a real biological system follows, and this equation, xt plus 1 is equal to r0 times xt 1 minus xt. So what are the equilibrium population for this model, this population model? So now how do we find that out? So we just have to assume that xt plus 1. I'm really sorry for the handwriting, but I hope that you are able to make out what I am saying, sort of what I'm writing. So we just replace xt plus 1 as well as xt by x star in this equation. Okay. And if we do that, what do we get? We get x star is equal to R0 times x star 1 minus x star. If there was an equilibrium population, then this equation must be true, right? So this already gives rise to some possible solutions here, right? So one possibility is, on the both sides you see x star, right? There's an x star here, there's an x star here. So one, immediate solution that follows is that x star could be 0. If the initial population size was 0, if I multiply anything with 0, I'll get 0, right? So that would be one possible equilibrium value. Okay. What's an alternative equilibrium value? That will then follow 1 is equal to R times 1 minus x star. Is that fine? Basically, I have now, assuming that x star is not 0, I have cancelled x stars here on both sides. So then I'm left with this equation. Okay. And if you solve this equation, correct me if I'm wrong. Okay, so you multiply this with this equation, and then I think you will get R minus 1 divided by R. Is that right? If you solve this simple algebraic equation, you find this.
Yes, sir.
Okay. So what we have found is that this simple model, which is also called the discrete-time logistic population model, has two equilibrium. One is that of 0, meaning an extinction population, and then it can also have another equilibrium, which is given by R minus 1 divided by R. Okay. Let us now go to the next page.
It's R not, right?
Thank you very much. Please keep correcting me with all my silly mistakes. Is that fine?
So can you repeat the last part again? It was not very clear. X
This
star equal to 0.
last step.
Yeah, x star equal to 0 after that.
So from this, okay, I can't see my pointer. Do you see my pointer now? Are you talking about from here? How did I get these two?
Yes.
Is that your question?
Yes, sir.
Okay, so let's just do it maybe slowly. Okay, let's go to the next page, and I will do it a bit slowly. So whenever you have an equation, how do you basically what I'm trying to do is there's an equation of this type now. X star is equal to R x star into 1 minus x. We want to find all values of x star when this equation is correct. Okay. When this, for example, if I now put, let's say x is equal to 1, will that be correct, by the way? If I put x equal to 1, what happens to right hand side? Right hand side becomes 0. Is that right? What happens to left hand side?
Yes.
It will be 1.
1.
So
1 equal to
is
0.
1 is equal to 0? Is that correct?
No.
It's not correct, right? So x star therefore cannot be 1. Do you agree with that?
Yes.
So let's now try x star is equal to 0. Left hand side will be 0. Right hand side will also be 0. Right?
Okay.
So therefore x star is equal to 0 is a valid solution for this. Okay. So that's how I found one equilibrium. Meaning if initial population was 0, it always remains 0, doesn't change anymore. That also makes intuitive sense, right?
Okay.
Okay. So that's how I found the first one. So, and whenever you have a mathematical equation, you also can simplify a few things, right? So basically now you agree that one possible solution is x star is equal to 0. Okay. Let's look for, are there any more solutions? This is a quadratic equation, right? Quadratic equation will usually have how many roots? It can have 2 real roots. So I have now found one root. You can now find another root using the standard methods that you may have learned in your high school. So what we can do is when you have an equation like this, we can cancel the terms, assuming that they're not 0 anymore. And then I will be then left with 1 is equal to R times 1 minus X star. Okay, is that okay? And then that is same as R minus RX star. Okay. And then you bring Rx to left hand side. Rx star becomes R minus 1. Bring this to left hand side. I'm just changing the positions of 1 and Rx here. Rx has come this side and 1 has gone that side. And that now leads me to this. Is that fine? And of course, I had already found one equilibrium here. X equals 0. Okay, now if you're not very sure, what you can do is go back to this equation and plug in X star is equal to R minus 1 by R. What you will find is that the left hand side will become equal to right hand side. Okay.
Okay.
That's one way to make sure you got the right answer. So basically, there are now two equilibriums for this population. One is extinction, the other one is a finite, potentially a finite population size. Okay. When is this positive, by the way? When is X star positive? It's positive if R is greater than 1. So again, this is R0. I have already lost 0 there. Huh? Okay, if R0 is greater than 1, this X star will be greater than 1. Okay. And it does make sense, right? You know, if R0 was less than 1, we knew that birth is less than death, and therefore extinction is a reasonable solution. So for you to have a positive equilibrium, R0 has to be greater than 1. Okay. So now what we will do next is we will now plot how did this happen? Okay, maybe someone's not going anymore. What is that? I don't know why.
Sir, I have a question.
Yeah, sure.
So the upper cap on so X star cannot take the value 1 because there is an upper cap on R0, sir, or?
Wait, well, I never said it can't take a value of 1.
Because from the expression, we get that X star is 1 minus 1 by R0. So if R0 is, extremely high, then
Strange problem. I have to stop sharing my screen and get back. Okay. Yeah, go ahead. You can ask the question.
So the X star's expression is 1 minus 1 by R0. And if R0 is tending, so R0 has an upper cap. That's why X star cannot assume the value 1, sir. Is that the reason, or?
Okay. So I'm sorry, I wasn't able to pay attention to your question. Can you please ask again? Why can't X star be 1? Is that your question? So there is a so in this model, you're right that X star cannot be 1. You're right. So what happens is that, you know, when X star does is 1, the right hand side becomes 0, right? And therefore consequently, whenever you reach that value of 1, the next population size is basically 0. And why is that happening? Because the way we defined this model is a bit peculiar, right? When we define this, R is equal to, let's go back to the first, you know, when we define that R is equal to R0 times 1 minus N by K, if R is a measure of resources in some way, which then causes birth and deaths, we said that when N is equal to K, R is 0, meaning the births and, deaths cancel out. And basically for every individual who is there in the current generation, there is nobody who is going to be there for the next generation.
Correct.
Right? Basically, everybody the current generation is dying, but they are actually not reproducing at all. So it's basically when N is equal to K, B is equal to 0 and D is equal to 1.
Yes, sir.
Right? Sure. That's why in this model you cannot reach a value of X equal to 1.
X star is 1.
So is it something like what, Germany, Japan, they say there's only aging population and it's I mean, there is no younger population, or the fertile this thing is less. It's something like that, is it?
Uh, no, this is happening because of a different reason, right? This is happening because n is very large. I don't think that's not the case in right. So this model does not distinguish who is old and who is young. Okay. So in this model, we are only assuming how the births and deaths depend on the population size, which we thought is a consequence of the resources available. It has nothing to do with the age of the population in this case. But that's another way what you are saying can happen. For example, you can have a very large population, but if everybody is old, you're right. And then again, you will have basically in the next generation nobody. But those kind of models are called age structured models, and that we have not incorporated in here.
Okay.
Vishu, you were saying these are non-overlapping generations, but they can be, right? I mean,
That's what I also said. Yeah, I said that mathematically they can be overlapping generations, but usually you think of them as non-overlapping primarily because by the end of one generation, so the parent generation is either dead or they are not fertile. Yeah. But that's not necessarily true all the time.
Okay.
So I think I lost one page. Somehow something happened to my screen or something. So I lost one page. Let me just rewrite the, but anyway, I had written the two equilibrium values. So there were two equilibrium, right? One is 0. The other one is R0 minus 1 divided by R0. So now what we do is, see, we have one parameter in this model, that only R0 is the only parameter here. So we want to know, and in fact, I had asked you last time, what happens to just, use your computer and Excel sheet to find out what happens to these populations, right? For different values of R0. So what we will now do is plot the equilibrium as a function of R0. Sorry, that's fine. So let's now, so what we have found is that X star is equal to 0 is always a possibility, right? An extinction is always independent of the value of R0. X star is equal to 0 is always an equilibrium. You all agree with this? Does this equilibrium depend on the value of R0? No, right? This is true for
yes,
all R0. So therefore, let me just write dotted line here representing this extinction, okay, of population. Okay, that's one equilibrium. What's the other equilibrium? That's given by R0 minus 1 divided by R0. What happens is X star when R0 is less than 1? That will be a negative number, and negative number has no biological meaning, right? Negative population size has no biological meaning. Therefore, I must look at this X star only when R0 is greater than 1. You all agree with that argument? So I will write 1 here. Okay, and before that, I won't even look at this. After that, I will plot this. It's R0 minus 1 divided by R0. What's the maximum value that X star can take? 1. Let's put that here. Okay, now let us write down. Let me now write this equilibrium, X star equilibrium for it looks like this. You agree? Okay, this is how basically these values are increasing with R0, but it is also saturating because it's 1 minus 1 by R0. So it sort of has a 1 over X kind of a behavior. So this is how it looks like. Okay. Now all of you are fine with this so far? And in fact, does this match with what you found in your analysis last Friday?
I have one question.
Yes, sir.
I know it probably does not make biological sense, but what happens when R naught is less than 0?
It does not make biological sense, therefore we will not answer the question. Is it fine? What do you even mean by saying R not less than 0, right? We said that the minimum value R0 can take is 0, right?
Okay,
So we
so
shouldn't
we
even
just
talk
don't
of
deal with
R0
that.
less than 1, 0.
Okay, so we just don't deal with that quality at all. Like
It's,
that.
it's basically the thing is, once you write down a mathematical equation, R0 can take any value, but not every value is biologically meaningful.
Okay, yeah, sure.
So we constrain parameters based on the biological constraints. Of course, if you just gave it to a mathematician, that person can do anything with R0.
Okay.
Right? But if you're concerned about applying this to populations, you have to say, okay, no, R0 cannot be less than 0.
Yeah, okay, thanks.
Okay. So, does this roughly represent what you also found? When R0 was less than 1, unfortunately had RM, it was my mistake. When RM was less than 1 in your previous simulations, you only found extinctions, right? Did you find a finite value, any of you? I don't think anybody would have, unless there was a mistake. And when R0 was greater than 1, and let's only focus up to 2 today, you found a finite value to which the population converged. Do you all agree to that? Did that depend on the initial condition? Yes. Whatever the value of initial value you chose, initial population size, did it depend on initial population size?
No.
It did not.
No.
Okay. So to represent that, we do the following. We sort of say, for example, let's stick to 0 and 1 again, because every population size you chose eventually landed up crashing here. We can write down arrows like this. Is that fine? Meaning whatever value of initial populations I choose, they will all eventually become extinct and X star becomes 0. Is that right? Likewise, for the blue line here, did you always find that they reach this same finite value for a given value of R0? For example, say you had chosen R0 of 1.5. Did you always end up with the same final value of population size?
Yes.
Okay.
Yes.
Okay. So is it reasonable to write like this then? If you had chosen a large value, maybe it will come down. Is that fine? No, I should not choose anything more than 1 here. That's why reduce the length. Is this fine? How about this red line that's lying down here? What about that? Did you find that for R0 greater than 1?
No.
No.
Why you did not find?
Something unstable.
But
No, it didn't go extinct. We saw something like it increased, then came back, and then hit saturation.
Okay. But basically, if it have reached some saturation, most likely, in fact, if you have done R0 for sufficiently fine value, you must check whether the X star that I have written down here corresponds to what you also found in a simulation, right? In fact, if you have a spreadsheet, you should just check what was the final value for that R0 or RM you had chosen, and then see, you can compare the values. Okay. But none of you found this lower branch, right?
When R was sufficiently high, we didn't get the lower extinction.
Let's be more specific. R0 greater than 1.
So when we take
It never went
X0
extinct.
equal to 1, we would reach that red line.
You would have reached red line if you had chosen X0 is equal to 1. Absolutely right. Very good point. And there is one more way you can reach red line. What was that? If you start with 0, right? There are only 2 ways you will reach this red line for R0 greater than 1. The one would be, let me write that down. If X0 is equal to 0, or if X0 was equal to 1. That is when you will reach this. For all other values of initial population size, you will always end up with the same, final value of population size, which should exactly match with this function we have derived today. Okay. Okay. So now clearly there is some difference between this red line here and the blue line here, right? There's something fundamentally different. Somebody used the word stable. Okay. And somebody used the word unstable, if I remember correctly, stable or unstable. So now can you tell me which one is stable in this regime for R0 greater than 1? Which of the 2 is stable, the red line or the blue line?
The blue one is
Blue
stable.
line.
The
Blue
red
one you think is the red one is stable. Which one? Somebody said red, somebody said blue. What should I choose?
Like for the
The blue
initial
one.
conditions and some specific cases, leaving those, blue one is stable.
So excluding these two very special cases, we will always end up with the blue, right?
Yes.
Okay. So you can say maybe this is a stable equilibrium population, right? Whereas this would be unstable. We will define this more carefully very soon. Okay. What about if R0 was less than 1? What is the stable population size?
That is 0.
That is 0, because any initial condition you began with, including 0 and 1, will go to 0. So usually when you write a diagram like this, which represents equilibrium values as a function of a parameter value, okay, you represent the stable equilibrium by solid lines and unstable equilibrium by dotted lines. Okay. So that's what I have done here, but I haven't very carefully defined what is stable. Shall we do that now?
Sir, in the
Can somebody define stability? Yeah, there's a question. Yes, go ahead, please.
In the previous graph, shouldn't you exclude the point 0 itself? Because I mean, the way we have defined x star will be 1 minus 1 by r0. So we need to exclude the point 0 and then start taking it from there, right?
They are both valid solutions to this quadratic equation, right?
Okay, you're taking it that way. Okay.
Right. They are both valid real solutions.
I had one question.
And then biologically, both of them make sense, right? If I start with an extinct population, it will remain extinct forever, right? If I start with a population which is R0 minus 1 by R3, it will again remain there forever. Yeah, so go ahead, Tarun.
So I didn't understand the part when x0 is equal to 1. Why does it have like go to extinction?
That's a very peculiar feature of this model. Okay, and it also relates to assignment question that's there. So I will let you think about this a bit. But let me also tell you, it's not biologically super meaningful anyway. So don't take that too seriously. But useful to just think within this model context why it is happening. So I will let you think a bit more. I gave an answer in one of the previous discussion points that somebody asked. So think about this a bit more. And maybe we can discuss it again on Friday. Maybe when you write down the assignment answer, what is the interpretation of K in that model, it might become more clear to you. Is that fine, Tarun? Is that okay?
That's cool. Tarun, yeah, right? I figured it was something related to the assignment.
It is related to assignment. Yes. Okay. So this is what we have. Now, while doing this, I actually haven't defined something called a stability at all. I have just somebody used the word stable, so I used it. So can somebody tell me what would a stable population mean? When do you call some population is stable and some other population is unstable? What do you think of intuitively when you hear the word stability?
A small perturbation should not be
same as rate of death.
Okay, somebody said small perturbation. The other person was saying
rate of birth is same as rate of death.
That is equilibrium, right?
So by stability, I wanted to mean that small perturbations should not shift the path of the equation a lot from the equilibrium value.
Sure. Okay. So what Raghuram said is basically definition of equilibrium itself. If the births equal deaths, then basically you have equilibrium. Okay.
But isn't that also right? I mean, isn't an equilibrium point also a stable point? Even from our plots, we see that, right?
That's a good question. Let's go back to this slide now. Do you agree that zero is equilibrium? Because if I start with 0 population, it will be always stay 0 here, right? In this range, above 1.
Yeah.
And if I start with this blue line, which is let's say R0 minus 1 by R0, again it will stay there, right? Both of them are equilibrium, but do you say both of them are stable? Not necessarily, because as somebody else said, we define stability based on not equilibrium per se, but what happens if I make a perturbation to the equilibrium. Okay, so if a perturbation dies down, we call that a stable equilibrium. Okay. However, if a perturbation grows, we call that unstable equilibrium. Okay, now with this definition, let us go back to
what
the...
is perturbation? I mean,
yeah, I'm going to define that. Okay, let's go back to this previous slide now. So, so in this graph, let us say there is this island which has 0 number of some mammals. Okay, and that is an equilibrium. All of you agree, because magically that mammal cannot come out of nowhere, right? So it will just remain 0 forever. Let's assume that Raghuram went and introduced few mammals in that island. Okay, so because now R0 is greater than 1 in this population, for this population in this island, what does it mean? It means the births are more than deaths, right? So even though he has introduced a small number of this mammals, what happens now? Because R0 is greater than 1, it will actually now start increasing. It means the population initially was equal to 0. Now it is going, and I have introduced small number of individuals, and then it actually now becomes to increase. Okay, now that means that the perturbation that Raghuram did is increasing with time. So therefore, 0 would be an unstable, extinction is an unstable equilibrium. It is an equilibrium because if it was there, it will always stay there. But if any perturbation that we have made now is actually going to increase the population size. Okay, let's say one another example one can think of is relocation that people do in the wildlife. For example, there is this talk of introducing some wild cheetahs which went extinct in India 100 years ago. There is talk of introducing some of this wild cheetah in central Indian landscapes. So currently it's in the 0 equilibrium. Okay, why are they thinking of introducing? They think that this landscape can actually sustain cheetahs. So therefore, if we introduce so therefore the extinction is an unstable equilibrium. Therefore, if we introduce some numbers, it will actually grow to some stable population size, which is actually a finite population size. Okay. On the other hand, imagine that it's already in a stable population size somewhere here. And if I now make some perturbation, let's say we are somewhere here, if I make now some perturbation in this direction, okay, what will happen to the population now? Will it go towards 0 or will it go back here?
Go back.
Go back, right? Because the births are greater than deaths here. So therefore, blue line is a stable equilibrium. So any perturbation I make, I could also have made a perturbation in this direction. Then what happens? It actually comes back again. Okay. So a stable equilibrium means the perturbation we make will actually decay. Whereas in an unstable equilibrium, the perturbation will grow with time. Is the idea clear now?
So this does not have any, external factors like whatever natural calamities, those they cannot be considered as perturbations, is it?
They can be. Why not? Why not? They can be very much. They are very much perturbations, right? So imagine a population of some species, okay, and it's in a forest, right? Now there are clearly climatic fluctuations year to year. There are day-to-day weather fluctuations, and those do cause deaths, right? Imagine if for some reason that was an unstable equilibrium. What should such fluctuations do? You should then take away to a different population size, right? But if we see that the population size are roughly remaining same over years, what can we say? Maybe they are, the natural perturbations that are happening in the landscape, that population is, stable to those perturbations. So therefore, it's actually a very useful concept. Now, although we are actually writing down an equation here, we wrote down an equation here which is deterministic. There are no fluctuations in this equation, right? There are no stochasticity perturbation here. But the idea is that the equilibrium that we derive from this model are still useful to think for real biological context, because if it is in a stable equilibrium, it will come back to that equilibrium again. Okay. So I hope the concepts of perturbations are clear now. Okay. So now how do we know whether an equilibrium is stable or unstable? Of course, if we have again a computer at your disposal, what you can do is, you can start with this population size, right? And then see it will, let's say if you have chosen a R0 of 1.5 and you can calculate X star, and then, it will just stay there forever. Right? Now, let us say I reduce the X star by some value, let's say 0.1 units. And then now we can check whether it actually comes back or not. So in a computationally, you know how to do. It turns out that you can also do this mathematically. Okay. So to do that, I will just tell you the formula. What I will do is the derivation of this. I'm going to just refer you to a video that that way I don't have to do all the underlying mathematics. Let's say you have this. We wrote this general equation, right? Times nt. Let us write down the entire right hand side as f of nt. Okay, basically the product of r and nt. Let us write the down as f of nt. Okay. So I think I have to use a new page. I don't have enough. Okay, so I'll just finish this and then we'll close the class. So let's now write down population size. The next generation can be in general written as this formula. Okay, so how do we define an equilibrium? Equilibrium will be when n is equal to f of n. Let's call the equilibrium population as n star. So because nt plus 1 is same as nt, this is the condition for equilibrium. So what is the condition for stability? I'm just going to write this down. I won't derive this. So most likely what I will do is I'll just send a YouTube video link sort of for you to go through the derivation. If the derivative of f with respect to n computed at the equilibrium population size, if the modulus of this is less than 1, this means it's a stable equilibrium. If not, it will be unstable equilibrium. Okay. So this is how we find the equilibrium and stability for a general discrete time population model. Okay, so this might of course seem a bit cryptic, and we will work out more examples of this and then see how to use it. And I'll also send you maybe a YouTube video, and we will do a bit more work on this in the sort of lab session on Friday. Is that fine? So we can end the class now, and we'll meet back again on Friday. Thank you very much.
Thank you.
Thank you.
Sir, I have a question.
Yes.
So when
But I have to leave now. I have another meeting.
Okay.
Why? Okay. So, but I can take one question and then I have to leave.
Sir, what about R0 is equal to 1? Why? So when R0 is equal to 1, number of births is equal to number of deaths, right? But then why the only possibility, the only stable, equilibrium possibility is 0 from the equation?
I don't understand your question. R0 is equal to 1 doesn't mean the entire. So okay, I have to share again. And I think part of it is probably the confusion I created because of inconsistent notation. If this capital R is equal to 1, that's when you have equilibrium. Okay.
Okay, sir.
Capital R is equal to R0 times some function.
Yes, sir.
R0 equal to 1 need not mean an equilibrium. Okay. So to make sure, I think today I have used consistent notations. Please stick to today's notations.
Okay, sir. Okay.
And does it help if I just share this one notes by maybe that way you just look at today's notation. I think I have been consistent in today's notation. Hopefully. Okay. If there are any mistakes, again, let me know. Okay. Thank you very much. I have to leave now. Bye.
Thank you, sir.
Thank you.